Welcome! We present a new method for de-rendering images of general 3D objects in the wild. By using coarse shape estimates instead of synthetic data and a novel weakly supervised loss formulation during training, our method achieves a very high level of detail. This enables various downstream tasks like relighting or further image analysis. De-rendering means to infer object intrinsics from a single image. It is the inverse of the well-known rendering step of computer graphics, where an image is generated from a similar set of object and material descriptors. In our method, we rely on the Phong illumination model. Several neural networks predict a per-pixel albedo map, normal map, and directional light parameters. From this decomposition, we can reconstruct the input image in two steps. First, we compute the shading effects as defined in the Phong illumination model. We consider diffuse and specular shading. In the second step, we combine the albedo map with both shading maps to reconstruct the input image. By modifying the lighting conditions, we can also relight the input image. Our goal in this paper is to de-render 3D objects in the wild. This comes with three major challenges. First, image de-rendering for objects is a highly ill-posed problem. Second, it is very difficult to obtain ground truth for in-the-wild objects. And third, there is no benchmarking dataset available. Previous de-rendering works generally relied on fully supervised formulations and a large synthetic dataset. Consequently, they have poor generalization capabilities to real objects. In our work, we leverage the insight that coarse shape estimates can easily be obtained for in-the-wild objects using off-the-shelf methods. We introduce a weakly supervised loss formulation that builds upon this insight and works on in-the-wild datasets. Therefore, we are the first learning-based decomposition method to overcome the need for large synthetic datasets and to achieve good generalization as we operate on in-the-wild objects by design. Further, we collected a novel photorealistic benchmark dataset, which we call COSY. Before training can begin, we use the coarse shape estimates to further obtain a coarse albedo and light estimate. Here we employ a simplified lighting model and optimize in a classical gradient-based way. Our novel weakly supervised loss formulation is made up of three components. The coarse loss is directly applied onto the predicted decomposition. This loss trains the network to predict a semantically plausible decomposition. A reconstruction loss between the input image and the reconstructed image trains the network to capture fine details and to encode them into the decomposition. By carefully combining those two loss components, we can achieve a semantically plausible decomposition that also contains all the details. As a third component, we also employ a GAN loss. A discriminator is tasked to classify for each reconstructed image whether predicted or randomized lighting conditions were used. For our experiments, we trained two models, one on Co3D, a large dataset of common objects in a 3D context, and one on CelebAHQ, a large collection of celebrity photographs. For Co3D, we obtained the coarse shape estimate via multiview stereo. For CelebAHQ, we used the unsupervised method unsub3D. Let's check out some results. On the left, you can see the input image, followed by the predictions. In the rightmost column, we depict shading and reconstruction under novel lighting conditions. The results show that our method is able to remove most lighting effects in the albedo map, capture the shape correctly in the normal map, and capture complex lighting effects very accurately in the shading maps. The reconstructions are very close to the input image. The relit results are also very realistic. Here, we perform relighting on a large number of examples. Finally, we also apply our method per frame on a video sequence. The predictions are very accurate and consistent over time. To compare to other de-rendering methods, we perform quantitative evaluations on our new COSY dataset. As shown in the table, our method performs overall best for both normal and albedo prediction. To conclude, we present a novel method for de-rendering 3D objects in the wild. For code, pre-trained models, and the COSY dataset, please visit our project page. Thank you.